relief. Those of you who've spoken up here, it's all squashed on this screen. That's good. So I'd like to give you an update of where we are with mini-RF Arecibo bistatic observations. Over the trick to this. Here we go. So right now we're in the middle of taking advantage of this unique opportunity with mini-RF acquiring bistatic data primarily to test the hypothesis that ice may be present inside some of the permanently shadowed craters. These data are resulting, as I'll show, in the first non-zero beta planetary images. These data will provide important independent evidence on the locations of volatiles in the polar regions, and it's only possible by having one of the two radars in lunar orbit, and I'll let you guess which one. So it's all about the bistatic angle. The bistatic angle is the angle between the transmit and the receive vectors for the two radars. It's also commonly referred to as the beta angle. You look at the image here in the bottom right, showing Arecibo and mini-RF around the moon. You can go in either direction, but we obviously are doing transmit from Arecibo, bounce off the moon, and receive on mini-RF. If you use the same antenna for the transmit and receive, then by definition you have a beta angle of 0 and you have what you have monostatic radar. This map here on the left shows the circular polarization ratio map of the moon that mini-RF acquired in normal SAR mode, where we acquired, this is obviously the data set we'll be comparing one of the data sets we'll be comparing the bistatic data with, and we acquired about 2/3 of the lunar surface, including over 99% of both polar regions. So the reason for this, one of the reasons for this, multiple data sets have provided evidence for volatiles in the polar regions, but mini-RF itself also played a contribution to this. Essentially, the circular polarization ratio is the ratio of the same sense that you retransmit a left circular polarized signal and you receive essentially, but that would bounce off a normal lunar surface and you would have a right circular polarized signal back. Under certain geologic circumstances, you can get more of the original left, in this case, sense back. So the CPR can be caused by both rocks and ice. The monostatic data show numerous craters, predominantly in the polar region, which have enhanced CPR values only in their interiors, which is very interesting geologically. Whereas the majority of craters on the moon, such as the one shown here on the right, you see a high CPR both inside and outside the crater with the ejector blanket because you've got a nice rocky, rough terrain. So high CPRs, these polar crater signatures are consistent with the presence of ice, but not uniquely so. And the bistatic radar measurements are a measurement which really could help to discriminate for whether they're caused by ice or surface roughness. So what does the physics say? Because we all know physics doesn't lie. This graph shows CPR versus beta angle. And so as I mentioned, at beta 0, you can have high for both rock in the red or an ice mixture in the blue. But as you get to if you have enhanced CPR because of ice, that's very much an opposition effect. And if you go out beyond, say, 1 or 2 degrees in bistatic angle, the physics predicts that your CPR should drop significantly. So to first order, what we're going to be doing is we're going to be looking at in this region, in sort of the 10-degree region, where we expect there to be a significant difference in CPR if it's for an icy surface relative to a rocky surface. So we've done bistatic before, I hear you say. Well, indeed we have. And so just to avoid the question, the Clementine mission back in '94 conducted a bistatic radar experiment where they transmitted and did for 4 orbits, 2 at the North Pole, 2 at the South Pole, and that signal was received by the Deep Space Network. They analyzed those data and published a paper saying that the data was consistent with an ice regolith mixture in the wall of Shackleton crater. Now, a couple of things why we want to do this again is, Firstly, that was a very controversial result, as probably many of you know, but also the data were essentially beam average data. They didn't make images, and we have the ability to make images. But wait, you've done bistatic before, I hear you say. Yes, so you also, a lot of ground-based bistatic radar, excellent bistatic radar mapping has been done by Bruce Campbell and others using Arecibo to transmit and typically the green bank receiver to receive. And you can see the image in the bottom left. They make very high quality data in sort of the 20 to 80 meter range. What we're doing, which is different, is because even though Arecibo and Green Bank are quite far apart, they're quite close together relative to how far away the moon is. So the bistatic angle for these data is essentially pseudo-monostatic. It's less than about 0.05 degrees. So we, like I mentioned, the key importance of our measurements is the fact that we can go out to sort of 10, 15 degrees for the first time. I told my parents not to call. So we conducted a low-power test of the system back in April last year with Arecibo in a low-power mode, 35 watts, and I shall come back to that power number. This was a proof of concept to essentially make sure that we could design waveforms so that we could distinguish between the different signals. There are different signals hitting the instrument. You have the key one, which has bounced off the moon in a backscatter mode and come back. You've also got the direct path where, because the Arecibo beam, once you get to lunar distances, is quite wide. So you've got the signal that hits the instrument, the back of the antenna directly, and some part of that will leak through. And you've also got a forward scatter component that essentially hits a sub-Earth point and bounce forward, again through the back of the antenna. So the results from the low-power test of our colleagues at Sandia, who do the processing for us, was very pleasing. This is just a Google image that they did to show where we're looking. But they were able to generate fairly low resolution. We weren't actually expecting images at all from this. We were just expecting wiggly lines. But they went beyond wiggly lines. And it really gave us a lot of confidence that once Arecibo was back up and running in high power, that we could take some very good quality data. Okay, so our ConOps is much more complicated than when we were operating in the normal monostatic SAR mode. Most of the things you see here, bullet type, actually happens in parallel. The first thing that we typically do when we're looking at a month of possible observations is we have to look at the times when Arecibo can see the moon, and assuming look, we have a database of key targets that I'll talk about next. So the first thing we have to do is what targets are available such that it's feasible to do an Arecibo LRO measurement in the desired beta range. We then also have to check on Arecibo availability. Arecibo is a very heavily utilized, it's a very good science asset, and we're very lucky to get some, to get time on it. We also then have to check that the mini-RF, we can orientate the spacecraft such that we can point our beam. It's not just a case of a vector. The orientation of the antenna has to be such that we want to make sure, for example, that no part of the beam actually crosses the ground track and things. So there are constraints on the way that we point. We also have to come up with we try and come up with a slew mechanism that can get LRO onto target in the right orientation without violating the sun constraints. I wouldn't want to go and see Mark Robertson's having to explain we pointed LROC at the sun, and neither would you. And finally, as all of this is going on, is that once we get more confident that a particular observation is feasible from a technical aspect, we coordinate with LROC and the LRO project and the other instruments. Particularly if our target happens to be visible when it's actually in sunlight, then that's trickier. We try and do these. If we have a choice, we do them when the target's over the nighttime hemisphere. But that, as you're not surprisingly, happens about half the time. And then finally, then we get to the magic day when we take the data, and now we're using Arecibo instead of 35 watts, we're using in a 200 kilowatt mode, which, if you're curious, is a lot more than 35. So the targets, we essentially to come up with what we hope will be a robust, when I say story, as in non-fiction, a robust story when we hope, with regard to an ice discovery. It's important, as I mentioned, physics doesn't lie, but it can mislead occasionally. is that one of the key things we actually have to do, we want to make sure we do take some regions which had high CPR in the monostatic data that we know aren't icy. Our goal is to take a few of the highest CPR regions on the moon where it's nice and rocky, and basically just show that the CPR stays high. And in fact, there will be some science there on the physics of radar scattering to see how the CPR changes with bistatic angle, because this hasn't been done before. And obviously our primary target is to take as many of the anomalous polar craters as possible. There are also, in part of Spudis's work, there's a handful of non-polar control craters which also have elevated CPRs only in their interiors. There aren't many of them. There are far more of them in the polar region, but to do a proper control experiment, we also need to take some of those and see what the CPR does there. And we also have, where possible, other high science value targets, particularly pyroclastic. There's some interesting science you can do with pyroclastic deposits. Okay, so where can we see? The Arecibo mini-Earth bistatic observations can image multiple areas of permanent shadow. This map on the right, which came from actually a different illumination study, this shows regions of the moon which are permanently shadowed from the sun, are shown in yellow and red, and shadowed from the Earth are shown in red and blue. And what are key are these yellow regions which are permanently shadowed from the sun, but at times can see the Earth. And these are obviously our key targets inside the anomalous polar craters. And here is an example of a snapshot using actually a tool derived for the illumination work. We can, for a given observation, precisely predict where Arecibo can see, which is shown in here for a particular example, and the regions in yellow are permanently shadowed regions that are visible during that collect. So quickly, because he's going to stand up in a minute, I want to show you some of our latest results. We took some high power data back in May. We took, as a test, we actually tried to do 2 collects because I showed the spinning plate slide. There's a lot of work that goes into planning one of these. So if we can actually, when we're fortunate enough to get an Arecibo opportunity, which is one of the biggest constraints for the amount that we can take, if we can try and take 2 scientifically interesting targets every time, then obviously it will double the return. And we were able to do that. So maneuver the spacecraft for the first collect, take the data, remaneuver the pointing for the second collect. So this was a South Polar collect. This is actually Shackleton here on the right. It's about 15 kilometers across. The data end up being roughly 50 meters per pixel. You can see it kind of goes from dark to light to dark, and that's really the first order. The bistatic angle for this strip goes from about 17 down to 10 and back up to 17. We were thrilled with the quality. Here at the bottom, we actually have a monostatic data image for comparison of the region. It's not orientated in the same direction. The green box shows you the same small crater, and this crater here in the monostatic is actually this one here, which is a small crater near Newton. And that was one of the targets. Actually, this crater here inside Short Crater was another target that has an interesting CPR signature. And even though I didn't pick the best stretch, which is something you're going to hear me saying a lot in the next 3 slides, we actually, you can see that this crater is this crater, and that we're really thrilled with the quality of the bistatic data, and hopefully it's only going to get better. So this is what we call an S1 image. Essentially, it's radar power. We also can make all the standard daughter products that we make for the science analysis. So these color ones here are the circular polarization ratio. One minor issue that we're just trying to get a handle on, and this is standard with regards to Arecibo, is the multiplicative noise, which essentially means that the noise somewhere in the middle of the take, where it's radar shadowed, is actually higher than the signal out here. So you can't just pick in, like with typical, if you're doing an optical and you want to get rid of the shadow, you can pick a DN value, you can say everything less than that, ignore. We can't do that here, because if you pick it based on that, you're going to lose all this. But there are methods that we're working on. It's known. This is a known problem. So unfortunately, what it does attract you with the CPR, your eye tends to get attracted to these really bright regions, which are in fact just the noise that's gone through the system. But the important thing here is that we can make the CPR, the maps, and the MCHI and all the other science products that we like to make. Getting closer. And it's not a definitive answer, because the CPR value in the monostatic data for the ejector from this crater was about 0.6, and we really want to take some stuff that's over 1. But even though it's subtle, I'm coming back to the didn't pick the best stretch, we actually do see elevated CPR in the bistatic of this ejector. We actually get a number of about 0.5. So we want to get places over 1, but at least to first order, we do appear to be proving, even with our first collect, that rough regions do stay high in the CPR if you go to bistatic. Okay, our second collect, this one I'm actually showing a quick context because it's quite a dull, flat region, which means the radar is kind of dull and flat. But this was taken predominantly, we wanted to try and take a second strip to test the procedure for doing 2, and the best science target available, because we really wanted the Newton collect, was actually this pyroclastic deposit inside sinus astium. He's coming. And again, this is the S1. Again, we're very pleased with the quality. And here's the CPR in grayscale and color. And one thing that hopefully you notice is the pyroclastic deposit really jumps out in the CPR. We know pyroclastics are lower in the CPR. We knew that from the monostatic, but we see it in the bistatic. And Lynn Carter on our science team, what part of her project is by having these data at 2 different bistatic angles, you should be able to determine the dielectric constant for the deposit, and from that you should learn more about it, such as potentially porosity and composition. So in conclusion, we have a good working system. We hope that these data will provide unique information on the ice deposits. They are the first planetary non-beta zero bistatic radar images, and we'll also learn about the lunar soil too. Thank you.
If we have